power system consists of synchronous generator and one synchronous motor, this one generator. With this data, actually this data is available on the generator nameplate. Okay, all these parameters are referring to this value. Okay, this resistance value, inductive reactance value is referred to its own rating. This one rating of the generator. This one transformer rating can be found on the transformer nameplate. Okay, so this circuit is a single line diagram. So now, can you draw the impedance diagram for this circuit? If you look at this, okay, for this case, we have generator. And then this generator have two parameters, resistance and inductive reactance. So we have to draw both of them. We have the resistance and inductive reactance for the generator. It's G. This one SG, this one RG. And then what else? We have, this box is actually the circuit breaker, but this circuit breaker is too big. Just ignore this box, okay? Usually the circuit breaker is small like this, very small, not big like this. We just ignore this circuit breaker. So we have the transformer T1. So we just draw the transformer. Transformer also have the resistance value and inductive reactance value like this. Is R T1 X T1. Okay. Then we have G1, T1. We have line 1, transmission line 1. Transmission line 1 with this parameter. You see, resistance value and inductance value. So we have this generator G1 X G1 RG1. We have transformer RT1 X T1. We have transmission line R and X, R transmission line, X transmission line, and then we have another transformer T2. We have this transformer RT2 XT2, and then we have we have load. Sorry, we have motor at the end of the bus. So this, just ignore this box. Okay, this is a circuit breaker. So we have motor M2 connected at the load bus. This bus bar. If we draw the bus bar, this is bus bar 1, and then we have another bus bar 2, and then we have another bus bar 3. Bus bar is the interconnection of the two or more components of the power system components. Let's say we have generator, we have transformer. So in the middle, we have one bus bar. So the connection between transformer and transmission line, we have another bus bar, and so on. This is bus bar number 3. Then we have bus bar number 4. So this load is connected at bus bar 4. So this is load. The motor. So the motor we can represent by this. This motor. So just ignore this straight line. This straight line is automatically come out when I try to draw. I try to write. I don't know why. Maybe because I push the wrong button. I don't know. So we have motor as inductive reactance for the motor SM, and this is all components that's available in this single line diagram. Okay, we have G1, T1, transmission line, TL1, T2, and motor. Look at this single line diagram. This is a straight line. Okay, so when we draw the impedance diagram, we just make a connection between the components. Okay. For the generator, we connect to the transformer, this T1. This one, transmission line 1, this one T2. And this one motor. So we just make a connection. Connect until this connection. But this circuit is not a closed loop. So we cannot do any analysis for the open circuit like this because the current will not flow. That's why we have to add the neutral line to close the loop of this circuit. Just add the neutral line to complete the circuit. When you add the neutral line, now the circuit is complete. Okay, then we can start our analysis. Okay, this is how we draw the impedance diagram. So you will get this circuit most of the time. But for the transmission line, we cannot ignore the resistance value because this resistance value is very high. Because this is cable, right? Cable from what the generation station towards the load center is very long transmission line. So when the transmission line, let's say this cable. So in chapter 3, you will study how to calculate resistance of the cable. Resistance of this cable, resistance value for the cable. Let's say this cable is 100 kilometers long. So resistance is equal to 0.001 ohms per kilometer. When the length of the transmission line is more than 100 kilometers, the value of resistance also increases significantly. Okay, maybe sometimes 0.1 ohms per kilometer. So this value increases as the transmission line increases. So we cannot ignore the resistance value. But in this transformer, usually the winding inside the transformer, we have winding, right? We have cable inside the transformer. This winding is not long enough so that we can ignore the resistance value because this resistance value is quite less. So usually we ignore this resistance value inside this transformer, this generator, transformer, and motors. But if given like this, you have to use it. Okay. Per unit system. What is the per unit system? Actually, the per unit system is the normalization techniques that we use to ease our calculation. Why? Okay, so we go. Why we have to use the per unit system? So something like this. So we have this circuit. Yes, we have a single line diagram like this. The power system network is not same as the electronic circuit. Because why? Let's say we have this same network. We have the load and the motor connected to the load bus. We have generator G1, we have transformer T1, T2, transmission line, and then load, and then motor. So when we have this type of circuit, we cannot simply or directly analyze the circuit by using this circuit. Why? Because the voltage level at each bus bar is different. Let's say here, at the generator station, the voltage supply is 20 kV. And then we have the step-up transformer. It's bus bar 1. It's bus bar 2. We have a step-up transformer. So to step up the voltage from 22 kV until, let's say, 500 kV. This one, we have another step-down transformer, 500 kV. Step it down until, let's say, 100, let's say, 11 kV. So if we look at this bus bar, the voltage at bus bar 1 is equal to 22 kV. This bus bar. Bus bar 1, we have 22 kV. Bus bar 2, this bus bar 2. Bus bar 2, we have 500 kV. Let's say this is bus bar 3, load bus bar number 3. We have 11 kV. If you look at the circuit, the voltage level of every parts of the circuit is not same. So when we convert this single line diagram into the impedance diagram like this, okay, now we have the impedance diagram. Let's say this is our impedance diagram. Okay, this impedance diagram. We have motor. Okay, let's say this is our impedance diagram. For the electronic circuit, current flowing in this line, let's say this I1 and I2 is equal. So in electronic circuit, we can say that I1 is equal to I2, right? But in power system network, current flowing in here is not equal. Let's say IG and let's say I load is not equal. IG is never equal to I load. Why? The question is why? Because the voltage level at bus bar 1 is 22 kV. The voltage level is different between bus bar 1 and bus bar 2 and bus bar 3. Let's say IG, we have voltage level 22 kV. At bus bar 3, voltage level is 11 kV. So current flowing in this circuit is not equal. IG is never equal to the IL in power system. So if we use this one, this impedance diagram to analyze electrical circuit, this one electrical circuit, we will get the wrong answer. So how to simplify our calculations? So first, we have to convert all the parameters into the normalized value, which is called as the per unit value. That's why we study the per unit value. We convert all the actual values into the per unit values. Okay, so that we can simplify our analysis, and then we can use the same technique as analyzing electronic circuit for the power system circuit. Okay, so we have to convert into the per unit value, this one, per unit system. Then we can analyze our circuits as the electronic circuits as usual. Okay, if we did not use the per unit system, as I mentioned earlier, you cannot simply say that I1 is equal to I2 because the voltage level is different. Okay, so for now, any question? Do you get my point?
Yes, sir.
Yes, sir.
Okay, it's good. So that's why we have to normalize all the values by using the per units values. Okay, so this is how we do it. So first we have to convert all the power system quantity into the per unit quantity. How to convert that quantity into the per unit? So we use this equation. So per unit is equal to actual quantity over base value. And this is the basic equation. So how to convert all the parameters into the per unit? We just use actual value into the base. So let's say Yeah. Okay, let's say this one. So we have this example. So we have this parameter. We have generator 1 with this parameter as G 0.5 per unit. This one as T1 they have 10%. 10% that means 0.1, also 0.1 per unit. For the transmission line, we have 220 ohms. This is not in per unit. So we have to convert this into the new into the per unit value. So XT per unit equal to actual 20 ohms over Z base. So Z base we have to calculate. So actual value over base value. This is the equation for converting actual value into the per unit value. But what happened to this one? This one is given in per units. Okay, this one also already in the per units. But this per units actually referring to this rating. 60 MVA. This one referring to 16 MVA. This one referring to 30 MVA. So although this one is in per unit, we have to refer to the same base. So we will see later what I mean by same base. Usually we will refer to 100 MVA base for all this per unit value. This one must be referred to 100 MVA. This one also must refer to 100 MVA. This one also have to refer to the 100 MVA. Okay. But for the transmission line, we have to find the per unit value for this actual value. Okay. So go back to the per unit quantity. So all the power system data or quantity, we have to convert it into the per units. Okay. All the parameters. Okay. Let's say for the power, voltage, current, and impedance, we have to express it by using per unit quantity, by using this equation. So let's say we have this parameter. S is the apparent power. Apparent power S, calculate S per unit, we take actual S over S base. This is base value. B is for base value, our base. Usually, to simplify our calculation, we choose one base to is our calculation to simplify our calculation. Usually, we will choose S base as 100 MVA. Most of the time, we use this S base 100 MVA, and then we choose one of the voltage bus bar as our base. So V base. Let's say V base 1. V at bus bar 1 as our base. For that case, let's say we choose 22 kV as our base. Okay. So by knowing these two base, we can convert all the parameters into the per unit parameters. For example, S per unit, V per unit. V per unit is V actual over V base. Same goes to I. I per unit equal to I actual over base. Per unit is equal to actual over base. Actual value over base value. So what we have to know is what is the base value for this case. For current, let's say. For voltage. For power. And for the impedance. Okay. So now this is three phase MVA base. Let's say this is single phase. S equal to VI. S per unit. So same as I per unit times V per unit and so on. So by solving this equation, we will get I base for single phase is given by I base equal to S base over V base. For the three phase, we will get this value. I think you already know lah uh, how to calculate I if S and V is given, because we know that for three phase S is equal to square root 3 V line I line. So to find I equal to S over square root 3 V over V. This is the basic equation for apparent power lah. That's why we get this equation. Okay, this is how we calculate I base. Why we have to calculate I base? To convert I into the per unit value, or to convert the per unit value into the actual value. Okay, this is the equations. So what else? This is Z or impedance. So impedance also same. So to get Z base is given by this equation. So Z base equal to V base square over S base. Where we get this equation? Actually from basic equation like this. So from this equation, we get this equation. Okay, so I will not explain further lah. You can look at this equation. Okay, for Z base and so on. So now come to the next subtopic is change of base. Just now we learned how to calculate or how to convert actual value into the base value. Now, as I mentioned earlier, if we have this circuit, let's say this circuit, okay, this circuit, okay, this circuit. We have this circuit with the parameter already in per units. This generator have Xg of 0.5 per units. This parameter is already in per unit. So can we use this per unit to analyze our impedance diagram circuits? Cannot, because this per units is referring to its own ratings. 0.5 per unit referring to the 60 MVA ratings. This one also referring to actually 10% equal to 0.1 per unit, referring to this value. This one 0.1%, 0.1 per unit referring to the 30 MVA. All the base is not equal. So we have to change these referring values. Okay, we have to convert this referring value into one standard values. Okay, so usually we'll take S base as 100 MVA. It's equal to S base. And this is our new base. So that we can convert this old per unit, we call this as old per unit. We have to calculate new per unit value. So we have to calculate new per unit values. That's why in these subtopics, we will learn how to change the base of the system. Okay, let's say we have the old value. This is a new value, Z per unit new. Z per unit O is actual value over Z base old. Okay, so when we convert it into the S base and square, sorry, Z base S base old over V base square, because we know that Z base equal to S over V base square. Sorry, V base square. So this one from previous, and this one from previous equations. Let's say this equation 2. So from equation 2, and this one from equation 2. So we have this relation. Z all per units given by this equation. Let's say this equation A. Z new per unit also the same. We have to convert by using actual value over Z base new. Just now Z base old. This one Z base old. The bottom part, and sorry, the upper part, the bottom part is Z base new. So Z per unit new is equal to this equation. Let's say this is B. Okay, by comparing this both equation A and B, okay, so we can get this relation. Z base Z per unit new is given by Z per unit O times S base new over S base O times V base O over V base new square. Where we get this equation? Actually, from solving these two equations. Okay, Z ohm, this one also Z ohm, we just solving this equation. So now I didn't go through this one. Okay, but if you solving this one, we will definitely get this equation. So what you have to know is how to convert old per unit value into the new per unit value by using this equation. Okay, so for example, we go back to the example one. Okay, this example one. So now we have xg per unit, but this is old value. So we have to calculate xg per unit new. So we know that z per unit new is equal to z per unit old times s base new over s base old times v base o v base new square. So this one you have to remember, otherwise you have to derive this one. But most of the time it will provide in the test and in the final exam, especially for this semester we have online test, so we don't have problem with the equations. Okay, so z per unit new equal to z per unit old times s base new, s base old, and so on. So what is this parameter? Okay, so for this case, let's say for the generator, we have xg per units old, this one. So x per unit old is equal to 0.5, is j, x is j 0.5 times s base new. So s base new, find the per unit value for xt1, xt2, and xt if the base value is 11 kV and 60 MVA. And this is s base new. So now s base new is 60 MVA. Or this s base old, this one, also 60 MVA. In this case, we have the same values. Okay, times V base old, V base old. This one V base new, V base new, V base 1 because V base at the generator bus bar, this one, V base 1. So V base 1 new is 11 kV. So V base old also 11 kV. So you get V base new 11 kV. This one new. V base O. This one V base O 11 kV. And square, because this one we can cancel it out and we will get the same per unit value for the generator. Okay. Okay, so far. Okay. Are you still with me?
Okay, sir.
Yes, sir. Okay.
Okay. That's how we calculate the new per unit for this component for generator. Okay. What happened to this one? Transformer. Okay. So usually before we start our analysis, so we have to convert this transmission line, this single line diagram into the impedance diagram. So first step, usually we draw impedance diagram. So second step, usually we find base voltage, find V base. Find base voltage. For each, I call it as a region, each region. Then we calculate new per unit value, per unit values. And then we can start our analysis lah, okay?